All right, just want to talk a little bit today about cotton sensitivity to drought stress. It's one of the topics that I'll talk about today. I actually want to cover a few things. So first things first, I'll talk a little bit about cotton response to drought stress. Following that, I'll talk a little bit about plant-based irrigation scheduling. We've had some really good talks in here today about, one, for the need for improving the efficiency of irrigation by irrigation scheduling, and then also basically some of the needs to look at in efficiency as well. And so first thing that I'll talk about, and actually some of this has already been talked about, but the need for irrigation. There's debate about whether you even need to irrigate cotton in the southeast. I've heard folks say this at a few meetings here and there. In arid regions, it's pretty obvious that you need irrigation. For one reason, there's high evaporative demand, so low relative humidity, high temperatures, and then there's low rainfall. So you've got these two things working against each other. You've got low rainfall and high evaporative demand. So a cotton crop that's grown in the desert southwest requires double the amount of water that the exact same crop would need in the humid southeast, for instance here in Georgia. So in humid regions, we have low evaporative demand, we have high rainfall, we have kind of that opposite situation there. If you looked at our yields from last year, you would say that, well, we really don't need to be irrigating. That's one possible conclusion you could come to, especially considering over half the acres are dryland acres in Georgia and in much of the southeast. However, that was an atypical year, okay? One of the things about irrigation is that you can decrease the risk associated with these episodic drought periods, and ultimately by decreasing that risk you can ensure that you prevent profit loss from year to year. So there is definitely a need for irrigation, but there's also a need to improve irrigation efficiency, scheduling efficiency or irrigation efficiency. We talked a little bit about this resource competition, so water's a finite resource. There was a little discussion about the water wars between states, the environmental concerns associated with reduced stream flows and such. And then there's the economics. It takes, for one, it takes money to pump water. All right, it takes energy. Energy translates into money, but also you can decrease yield in cotton by over-irrigating. That's one thing about cotton is that if you're above that threshold, it'll just continue to put on vegetative growth and lose bolls, and you can actually decrease yield. So there's economic considerations as well. One of the things about cotton is that it's primarily limited under drought stress. So heat stress is a whole other thing. There's different stresses a plant can encounter during the growing season. Drought stress primarily limits yield by limiting source strength. And when I talk about source strength, I'm talking about the total leaf area that's out there and how efficient it is, how photosynthetically efficient it is. That's the main limitation. And despite all the research that's been conducted over the past several decades, there's still a lot of debate about how drought stress affects photosynthesis in cotton. So to sort of address this, what I did when I first came here is established a study where we had, and actually I worked in with Guy Collins on this, but utilized his most extreme irrigation treatment, so the 100% Checkbook, which you've heard mentioned already today, the dryland treatment, and so these two are extremes, okay? And then I had 3 cultivars in there, and I'll say up front that there really were no differences in the interaction between cultivars and irrigation treatment, so that either means that they're just not different in their response to irrigation or that the stress wasn't severe enough. So that portion of the talk, you're not going to see much about cultivars when we move through the talk today. Okay, so I had these different extremes, and basically threw everything that I knew to throw at it to measure how the plant was responding under drought stress. So canopy temperature, you can see infrared temperature using thermocouples. Water potential, that little blue box there measures what's called water potential. That's a direct measure of crop water status, both pre-dawn and midday water status. That fluorometer there on the far right, upper right-hand corner as you're looking at it, that measures those light reactions of photosynthesis. If you can remember back to your high school biology, the light reactions of photosynthesis. So that's those initial processes. The green box, we'll call it the green box down there, is a an infrared gas analyzer. It'll measure CO2 exchange, so it measures net photosynthesis, and it'll measure stomatoconductance, it'll measure transpirational water loss by the leaves as well. And if you combine that with that fluorometer up there, you can get all kinds of data. You can get photorespiration data, which is wasteful, basically burning the carbon that you've already made through photorespiration. It's actually a wasteful process. It's an inefficient process. And so rather than go through a whole bunch of data slides like I did last year, I'm going to summarize in just a general table. So net photosynthesis is the total, and this kind of summarizes everything, but net photosynthesis is that carbon that's available for growth and maintenance. Okay, that's what the plant actually fixes. It's available for growth and maintenance. All right? That is affected by a number of things. So the first thing is those pores in the surface of the leaf called the stoma. They close under drought stress. That's probably one of the most sensitive things is what we've found. And when that happens, it decreases CO2 availability inside the leaf, and it increases photorespiration. So two things. There's less CO2 inside the leaf, photorespiration increases, so you have less substrate for the reaction, and you also have an increase in burning the carbon that you already made. So gross photosynthesis is decreased by those two things. Okay? Then you take that carbon, that's what you have to work with, and that's decreased even more as a percentage by dark respiration. So just the normal everyday processes that the plant undergoes, the percent of that gross photosynthesis, there's more of it that's burnt up in the process of respiration. So that's the next thing that happens. What we have found in the last 2 years of studies is that electron transport, those light reactions, there's a lot of information on this because it's a pretty quick measure that people can get. We found that that's relatively insensitive to drought stress. You have to have a very severe stress to see anything. We haven't seen it in the past 2 years. So anyhow, if you're looking for something that's really sensitive to detect drought stress, that wouldn't be the measurement that you'd be after. So anyway, this is just kind of and then of course we had decreased lint yields, but again, looking at these parameters that showed responses, I had this slide up last year as well. Each data point actually represents 12 replicate plots there, so it's not just, 6 data points. That central, all of these parameters, so infrared canopy temperature on the left, and as you move to the right, pre-dawn water potential, midday water potential, they all correlated really well with net photosynthesis, which is on the y-axis here. So they all could be predictive of photosynthetic response. So any of these you could potentially utilize as measures of crop water status. But what I really want to point out, though, is that the center one there, the pre-dawn water potential, that because it's measured during pre-dawn hours, it's not subject to the same environmental variability. We don't have the same problems. We don't have to worry about cloud cover at midday. The problem is you've got to be there at pre-dawn. You've got to be there a couple hours before daylight and do your measurements. That's the only thing. It's an inconvenient measurement time. However, it's subject to a lot less variability due to cloud cover and other things that happen throughout the day. All right, okay, I had an extra slide there. So then what I want to do is move into talking about plant-based irrigation scheduling, a little bit of what we've done over the past year. And I've got to include this slide because I've heard it, and this is not a producer saying this. This has been at meetings where we've had research scientists, and I've had them, and sometimes I don't say anything, but there's a general statement that you'll hear, and it's, we already know how to irrigate. I can look at the crop and tell you it needs water, right? I mean, I've heard this multiple times at meetings. If you can look at the crop and tell me that it needs water, then you've probably already lost some yield. And that's kind of the point I want to make is, that's not the kind of plant-based scheduling I'm talking about here. But this comment is made routinely, is that we already know how to irrigate. So George and myself and Calvin and other folks like us, basically we'd be out of a job, right? We don't even need to be investigating this anymore. I would argue that no, we still have some work that needs to be done. So here's just some general, this is not plant-based methods, this is just a very quick overview. George covered some things earlier. I can't really go into that kind of detail because it's not the focus of the talk, but this is the checkbook method. That checkbook method says the cotton crop in a given week of development needs a certain amount of water. You subtract the amount due to rainfall, and you supply the balance, you supply the rest with irrigation. Very simple approach, and you can include information about soil water holding capacity along with that to get a feel for when that will be, that reserve will be depleted. Soil moisture sensors, there's a few different types of soil moisture sensors that could potentially be used. It's very promising in terms of automation based on actual measured parameters. And then what I want to talk about is we have a plant that's growing out there that there's a lot of different things going on that will impact the water status of that plant. There's the atmospheric demand, okay? So that could vary from day to day. There's soil properties, there's rooting depth, and he talked about rooting depth. Those are estimates of rooting depth, right? And as good as that is, you know, the plant may have different rooting depth. Soil structure, not just soil, a lot of the water holding capacity is based on soil texture. There's soil structure, there's soil organic matter, there's management aspects that change the amount of water in that soil profile that's actually available to the plant. That ultimately only the plant is going to know what's available to it, right? I say no, I'll use put in quotation marks. And then there's the plant itself. How big that plant is, how much leaf area it has, stomatal characteristics, so how many pores are out there giving off water. There's all these things that ultimately come together, and the plant integrates all of these factors into the water status of the plant. So anyway, in theory, you could use this ultimately as your sensor if you knew the right measure, right? So there's all kinds of things that could be measured. I'm not going to go into an extensive review or anything. I'm going to focus mainly on the research that we've conducted. To address this, I always say we because I'm never working alone. I mean, I'm working with Lola, I'm working with Daryl as my graduate student, a bunch of other folks. So when I get up here, I'm not just talking about I did this, I did that. I tend to say we did this, we did that. So anyway, that's just what I do. But anyhow, there were 5 irrigation treatments, a couple of cultivars there. There was the 100% Checkbook and then dryland, and then 3 Predawn water potential triggers. You can see these here, okay? 3 Predawn water potential triggers, okay? And so basically 3 times a week we measured Predawn water potential, and then overlaying this entire thing, there were also infrared canopy temperature sensors. So I'll talk a little bit about that. If you look in A, that's the trend in Predawn water potential. Throughout the growing season, you can see we only crossed that highest threshold a few times during the season, once early on and then a couple times later in the season.
John, which part of the plant were you measuring? Which part of the plant?
That's the 4th, and it was actually in that previous slide. I didn't talk a whole lot about it, but that was the 4th main stem node. It's the leaf. You cut the leaf, you measure water potential of the leaf, okay? And you do this during Predawn. Theoretically, that Predawn water potential should be in equilibrium with, and it actually doesn't work this way, but it's the maximum water potential that plant's going to see for the day, right? It's the maximum diurnal water potential that plant will experience. We used to say that it is the soil water potential in contact with the roots, essentially, because everything equilibrates at night. They're finding that's not entirely correct, but it's close, okay? Now, you say, well, why don't I just use a soil moisture sensor? That's a fair, I know you didn't say that, but that's a fair question. I've heard lots of people say this, but ultimately it's whatever that plant's experiencing, right? That's the key is whatever those roots are experiencing, it's that water potential. So anyhow, yeah, so we're actually measuring leaves here. This is leaf water potential, but it's just measured during Predawn hours. You can see some of the temperature trends throughout the season, and then in C here, the leaf minus air temperature trends. Now, I want to just kind of move on. This is just showing some of the data. You'll see some skips in the data there. That's where that's a week where every time the morning that we would plan to go out and do these readings, we'd have all kinds of rain in the morning. So that is one drawback. You can miss some data because essentially you're getting flooded out that morning. But again, that's pretty much the only situation in which we weren't able to get data. So Predawn water potential, if we average for each plot and we look at it throughout the season, there's nothing real exciting there. It's all pretty high water potentials. Everything pretty much reads the same if you average again throughout the season. So I'm going to move through these last pretty quickly because I'm sure I don't have a whole lot of time left. But this one, don't focus too much on worrying about what this is or everything. This graph is the response of a well-watered crop to a range of vapor pressure deficit. In other words, relative humidity and temperature, okay, vapor pressure deficit. So we can, with a pretty decent amount of accuracy, each one of these data points represents 8 replicate plots. We have to be specific about the light intensity and all that kind of stuff. But ultimately, we can predict what a well-watered crop, how a well-watered crop ought to respond to vapor pressure deficit. Once we've developed this, for any given point in time, we can calculate the crop water stress index. Okay? As long as we have this data, we can calculate the crop water stress index. These are our upper limits. I just put some examples on here. Don't worry about that. These are the upper limits, and this is the baseline for a well-watered crop. Anything in between here is at some level of water stress, a value between 0 and 1, essentially. You can overshoot, obviously, or undershoot here. But what I wanted to point out is if you look at the data averaged throughout the season, everything hovers right around 0 water stress. All right? If you just look at it as an average throughout the season, obviously, it's like anything. If you looked at the Predawn water potential data, you saw some points where we needed to trigger some irrigation. This is just to sum it all up into one figure here. If we looked at plant height, it was showing us that there was no difference throughout the season for these irrigation treatments, and yet we applied different amounts of water. So our checkbook approach, we applied more water than any of the other approaches. You can kind of see a little stair step here, and then ultimately these last two we didn't apply any because we never crossed those thresholds. If you look at here, 66.9 centimeters of rain. Now, we need 46 to grow, during the summer to grow a decent cotton crop. So we got a lot of rain throughout the season. Obviously, it's also associated with distribution throughout the season and everything. But you can see that we did apply different amounts of water. So on to the most important thing we want to talk about here is yields. Yields weren't different for these treatments. But you can see because we applied different amounts of water, we had differences in water use efficiency. Now, of course, you look at the dryland. This is one of those years you could potentially say, well, we don't need to irrigate. We just had so much rainfall this year. But the take-home that I want is that we can use, I guess I got to go over the acknowledgements. I got to thank obviously the folks that who are helping fund this work, and then, of course, all the people that are involved in the project as well. And then before I go into the questions, I just want to say, I think this really tells us that we can use these plant-based methods to improve irrigation efficiency, and if we use it in conjunction with sensor-based methods, and that's one thing I didn't include in here, was I had some watermarks in these plots as well, and I only was able to represent basically 2 reps, but as an average, if you looked at it throughout the season, it showed the same trends as the Predawn water potential, so it's pretty interesting in that regard. Anyhow, I think if we take these sensors that give us the ability to automate the entire process, and we lay it over with these plant-based methods, or I would say with the approach that I'm using here, we can define what our thresholds need to be. For instance, for these canopy temperature sensors, and potentially completely automate this system in the future. So with that, if you have any questions, I'll take them right now.
About 1 minute.
Huh?
Got about 1 minute.
I got 1 minute. Okay. I didn't think I did.
If you look out and see a field is wilted,
Yeah.
does it always need water? Is that the problem?
If it's wilted, it needs water. That's not saying that if you see, let me back up, and I didn't specify this. So let's say you see one that's wilted. Do I need to irrigate? Yeah, you need to irrigate. You do need to irrigate. The thing is, you don't necessarily have to wait until it's wilted to irrigate. That's the point I'm making, is most of these folks are saying, well, I can irrigate based on what I'm seeing. Well, if you can see it's wilted, you've probably lost yield, at least some yield, by the time you see that wilting. Now look, if it's wilted, yeah, you need to irrigate. And that's been my experience. If I see plants wilting, because we have this range of thresholds, right? If I've seen plants wilting under these thresholds, and the thresholds are telling us, hey, we need to irrigate. So yeah, absolutely. You do need to irrigate if it's wilting. However, it's best not to wait until that point. So I guess that's about all the time I have for a question. So anyway, thank you.